Good afternoon, everyone, and welcome to the Kleinman Center. I'm Angela Pachon, the Research Director of the Center, and I'll be your host and moderator today for this panel of experts discussing a topic that keeps electricity people awake at night, is the reliability of the electric grid. So, aging and insufficient transmission infrastructure, extreme weather events, delays in the interconnection of new renewable projects, as well as decarbonization targets and policies coming from the federal government and from the different states that are accelerating the retirement of fossil fuel power capacity have all converged to create a perfect storm. And this occurs at a time when demand is steadily increasing due to the electrification of various sectors and the growing electricity requirements of the digital economy. So over the past 3 years, we witnessed supply shortages in California, Texas, Tennessee, and North Carolina. And just last December, here in the PJM area, we narrowly avoid outages following a winter storm. So this is to say that reliability has become a paramount concern for everyone. And to the point that, the topic has the attention of FERC, which is holding a technical conference tomorrow. And but lucky you don't need to travel to Washington tomorrow, because we have assembled this panel of experts to really delve deeply into this critical issue and examining the challenges and solutions that will define the future of the grid and its reliability. So let me introduce our experts today. We have first Kelly Joseph. Kelly is a fellow of the Kleinman Center. She works at the intersection of policy and markets with a focus on transitioning the electricity sector to support a decarbonized, climate-resilient economy. She is an expert on electricity market design, electricity regulatory policy, utility rate design, power system economics, and gas and electric coordination. Kelly holds a PhD in political economy from the University of Virginia and a master in sociology from the University of Virginia and an MBA with a concentration in finance from IE Business School in Spain. Then we have John Moura. John is the Director of Reliability Assessment and Performance Analysis at the North American Electricity Reliability Corporation, NERC. He leads the Electric Reliability Organization efforts to independently assess and report on the overall reliability, adequacy, and associated risk of the interconnected North America bulk power system. He is co-author of numerous NERC special reports and several technical publications. John earned his bachelor degree from Rutgers University. And last but not least, we have Adam Keech. Adam is the Vice President of Market Design and Economics at PJM Interconnection, where he oversees the design of all the wholesale markets operated by PJM and the development of large-scale advanced analyses, such as those done for carbon pricing and renewable integration. He earned a Bachelor of Science in Electrical Engineering from Rutgers University and earned a Master of Science in Applying Statistics from Westchester. Please join me in welcoming our panelists. And without further ado, let's get started. We have a format where our panelists are gonna to make a brief presentation to introduce the different aspects of this topic. And after their presentations, we can start a moderated conversation. I will have some questions, but then we will open the floor to the audience. So let's get started.
All righty. Good afternoon, everybody. Thank you for joining us, and thank you so much for the invitation to be with everybody today. I'm John Moura. I'm the Director of Reliability Assessment, and my focus is looking at reliability each and every day. That's what I've been doing at NERC for just about 15 years, and I'm privileged in a way where I get to publish 4 different reports per year that really help us understand the risks and the associated threats to the bulk power system with, of course, the reliability perspective. We look forward, so we're looking at 10 years. A lot of that's looking at the projected resources, the emerging risks, what the transmission system looks like. We have some seasonal assessments that look out just the next couple months. In fact, we're publishing, it might actually be posted to our website, just now, is our latest winter reliability assessment that gives you a forward look over the next couple months about what we anticipate the conditions will be for the next winter. We also do summer assessment, and we also look backwards to look at the trends over time. So these 4 reports really give us that forward, the near term, the backward trends, give us a really good perspective of reliability. The other thing that's part of my organization is the event analysis. So when big things happen, we do the forensics around the events, kind of like the NTSB, right? For electrical events, and that helps us learn things about how things break and how we need to accommodate the system to prepare it for the resources we're seeing in the future. Also, little things that happen to be important. We see those every now and then. So what I basically wanted to talk to you a little bit today is the interconnected system and the risks we're seeing in the future. And before we talk a little bit about the future, I wanted to set the table a little bit to look at the historical past and what's happened over the last 10 years. And the system has a storied history back from the 20s and 30s around how we interconnected and the value of interconnection and why we interconnect for cost and for reliability perspectives. But over the last 10 years, the system has been quite stagnant. If you just look at how much capacity on the system we've actually built, none. We've actually reduced overall capacity in North American bulk power system by 4%, right? So we have less resource. We built a lot of resources, but we have less total resources available to us as a grid. So that's one part of the equation, right? How much resources on your system. Other part of the equation that's super important is the demand. 3% increase in demand over that same time period. So we've increased demand over the last 10 years, but we've reduced total resources. And so if you've been paying attention to any of our reports, you are aware of the risk in the future. And so it's no surprise you see these risk maps in our latest assessments that point to where these challenges are. Resources are getting tighter, our reserves are getting tighter, and year after year, we've seen that we're more reliant on the interconnections than we really ever have. We have less resources in each individual area. So when you have less resources in each individual area, you're more reliant on your neighbors. And what we're seeing more recently is when you're relying on your neighbors and your neighbors have reduced their capacity as well, now you're reliant on those neighbors' neighbors and those neighbors' neighbors. And the key to that is transmission. And that's something that's really been stagnated in our country for quite some time. So some recent examples. I was also privileged enough to publish the FERC NERC inquiry on the Winter Storm Elliott. And of course, we also saw the Winter Storm Uri event from a couple of years that really hampered reliability. We saw the devastation in both those examples, but it's kind of clear here around why we need to understand the risks and and we have to have understanding for energy that we're relying on in different parts of the country to serve our mix. So here's a good example. Between ERCOT and MISO, so basically the middle stretch of the country, there's about 60 gigawatts of wind installed. So you count up all the wind turbines, 60 gigawatts of wind. On June 6th, that 60 gigawatts was producing 300 megawatt output. right? And so it's a significant decrease, and you can kind of see. Do I have a laser here? There we go. I'll use my. I use the one my dad gave me. Right over here. You see this right here? Boom. It's basically 60 gigawatts going down to 300 megawatts. And so think about that from an engineering perspective, right? You think about these design criteria, right? If you think about building a building, right? What does the building need to be able to withstand? Wind, wind forces, number of structural forces. This is a very similar thing. The system needs to be able to withstand the loss of wind, right? And so we need to plan the system, understanding that we're going to have these hours every now and then, no matter how rare they are. This is the key for reliability. We need to be able to build the system to withstand that level of loss. It happens. We expect it to happen in the future. And that 60 gigawatts in a very near future will be 120, will be 200, will be 300. Hopefully we were able to build that out and transfer that power where it needs to go. But on a future June 6th, that 200 gigawatts would also get down to 300 megawatts. So a significant aspect that we need to plan and design around. Another example more recently, and Adam will talk probably a little bit about this, but during these extremes, right, when we're more reliant on our neighbors, we've seen more recently the need to cut those transactions to support local reliability, right? So the very reason we're interconnecting, the value of reliability, the value of reducing cost is being hampered under these extreme conditions. So we really need to understand those. And you know, we're really used to having a very high level of reliability in this country. This is a chart I like to show that shows the amount of hours without firm load shed, right? When the system operators are shedding load, it essentially means they're out of options. They're looking for any option to get more energy. And after that call has failed, they have to resort to some load shed to balance the supply and demand. And so for years and years, we're used to this metric being 100%, you know, 0 hours without operator initiated load shed. And so the trend is clear. We're seeing more hours. In 2020, we had 22 hours across the interconnected bulk power system in North America that had operator initiated firm load shed. In 2021, it was 70 hours. I think in the 2022 number, you'll have also another big number. So the empirical evidence that we're having more problems it's not just rhetoric, right? We're actually seeing these challenges. And the reason for the challenges are very similar, right? Year after year, we see the same types of challenges, especially during the cold winter event. And so there's a couple real important things to understand about these winter events, and the three major things that are challenging the grid operators. One is the significant level of unplanned generator outages. And so about a third of generator outages during these cold weather events are due to they simply didn't have gas, right? And there's a lot of ways in which those generators get there, but you'd be surprised, and maybe a lot of you know this, but not every generator out there has a firm commitment, a firm contractual arrangement to get natural gas. That's pretty US, it's kind of a special thing in the US. If you look at our Canadian counterparts, they're not aware of what non-firm gas is. Everything's built firm. And so because of that, on the most extreme cold days, when all the firm contractual rights are being called upon, the generators that are essentially flying standby don't have a ticket, and so they come offline. There are a number of mechanical issues, especially in terms of winterization that happens to these units as well. So another third is due to mechanical failure. Winterization, you know, the units that we're using, that we're relying much more often, combined cycles, combustion turbines, much more sensitive to freezing. The mechanics the metals are different. The computer system and controls are digital. And it's just not as robust and resilient to extreme weather that, you know, some of our older plants, maybe coal or nuclear units are. So we have to understand those challenges. We have to be able to winterize those. But it's not as simple as just winterizing. You can't just buy a winterization package for a unit in Texas because it doesn't exist. These units are outside. They're designed to be outside. They're designed to be cooled by the ambient temperatures. And so when you put winterization, the insulation, all these, heat tracing around that, you actually have to remove all that during the summer to make sure the unit can actually operate. And so you can put it on in the winter, but when do you put it on? There's a logistical challenge if you get a cold spell that happens early. So there's some challenges. There's human error involved in that. And then the last thing is the short range forecast for peak electricity demand. There's a couple of things that are going with electricity demand. First is the significant increase over the next couple of years. If you look at our long-term assessment, that's going to be published in a couple of years, the growth rate for electricity demand has doubled in the last 2 years. And so a significant future of more electricity being transitioned. I just bought an EV. That's a 11 kilowatt peak demand that I added to the Georgia Power peak demand that I never told them about. And so these are challenges. By the way, 11 kilowatt demand is my EV. My whole house peak demand is 6. If my wife gets one, I mean, this is a runaway trade. And I'm not like, I'm worried about EVs. I was worried about it that I bought it. I'm making an economic decision and it's actually quite valuable. I think others will make that very soon if they haven't already. So EVs are certainly coming in. There's others. There's the demand centers. There's the crypto mining. There's so much demand out there, and it's actually kind of being throttled a little bit. We can't bring on from at the load serving entity level large demand. So, and then of course in the South, the types of heat we have, where we're seeing these challenges, usually resistive heating. So it's like a toaster. It sucks up electricity. So these are and that's where a lot of the population has gone. So those are the trends we're seeing from a winter perspective, but really it's all about this hyper complex risk environment. It's not just the winter. It's not just the resource mix changing. There's so many different interplays at hand. The rapidly changing resource mix. We have a lot of retirements occurring over the next couple of years. What we know is going to retire 90 gigawatts. That's what we know is already planned to retire. And you already saw my chart around our risk map, right? That'll just make things tighter. Energy and electric policy, environmental policy driving a lot of the energy policy we're seeing. We think that there should be a voice for energy policy. A couple things on these hyper complex risk environment. Natural gas, renewables, we're counting more on those. They have a different resource production profile. Natural gas, pretty good, but again, the contractual issues, it's just in time fuel, right? You can't go in your backyard and say, I've got, 1 month, 2 month, 3 month of piles of natural gas. It's a just in time. So those are some challenges. And then the last thing I really kind of wanted to mention, I won't talk too much about the cyber and physical, very important risks. But the last thing I really want to talk about are essential reliability services. So I'll end it with this story. I bought a 4,000 watt generator. I felt like I needed it for my house. Okay, so I said, this should certainly be able to power my 2,000 watt air conditioner, right? 4,000 watt generator should absolutely power my 2,000 watt air conditioner. Well, when I get everything running, plug it all up, it wouldn't start. Well, why is that? It's only 2,000. This thing's rated for 4,000. And the difference is essential reliability services. These are the things that the grid has that isn't available from every type of generator. There's a startup, there's a surge load for that air conditioner. It could be 3, 4, 5 times the rated normal load. That's things we just get from the grid for free, right? These are the things we really need to start thinking about. How do you price that? How do you ensure these essential reliability services remain when a lot of the resources that provided that, just based on the physics of their machine, are retiring? So that's really the missing reliability piece that we've got to figure out going forward. So I know we have more discussions with Adam and Kelly, but I'll be here back for questions. Looking forward to it. Thanks.
That one. Will you have background slides?
Yeah.
I don't want to give away your
Oh, there's so much good stuff.
all your main points. I'll do it fast. I don't want to steal a show from you. Good afternoon, everybody. My name's Adam Keech. Just to reorient you, I'm from PJM, which is the regional grid operator for the Mid-Atlantic area of the United States. My job specifically is wholesale market design. There's another set of responsibilities I have as well that goes into advanced analytics and producing reports and things like that. But I'm going to focus on market design and just start with thanking John for setting this up. A lot of the things that I'll talk about, especially starting on the first slide, get back to reliability. If you take nothing away from what I say, the purpose of markets is to motivate market participants to act in a way that promotes reliability. And it's to tie the financial incentives into that. So if you don't remember anything else I say, write that down on your hand, do something. That's the one thing I want you to remember. We are here to promote reliability. That is the main purpose, right? And for markets, the additional purpose is do it cost effectively, right? And so when we talk about market design in PJM, we always start with as good of an explanation of the problem as we can. Because if the description of the problem is a little fuzzy, the solutions start to deviate and we end up in places where we have solutions to problems we don't actually have. So the way we start thinking about it is, what is the problem that the grid operator is experiencing? And in the context of the energy transition that John talked about, there's a handful of different things that if you're a grid operator and you were a grid operator 10 years ago, you're probably looking at the system going, man, things are a little bit different than they were maybe 10 years ago, right? You're seeing increased penetration of renewables. He talked about the swath of wind in the middle of the United States. In this area of the United States, it's not quite as prominent as it is further to the west and also to the south. But it's growing. The bottom left corner of this slide is what we call our interconnection queue. Now, the interconnection queue is what are all the types of generators that are next in line to get built and put on the system. There's 230,000 megawatts, right? To put it in perspective, the peak load of PJM is about 155,000. So you've got roughly time and a half-ish, not quite. And only 2% of those are the conventional resources, natural gas, that we've relied upon for decades and decades. The other 98% are storage. They're hybrids, they're wind, they're solar. And so the demographics of the generation fleet is changing quite dramatically. Now, like I said, it's a little slower in PJM than it is in California. But I mean, you look at the chart, you can see it's coming. The question is really when and how quickly it gets here, right? So more renewable resources that are subject to uncertainty and really forecasting weather. You look at the weather in the morning and it's different than what you thought it was going to be in the afternoon. It's the same kind of deal with renewables. You think the wind's going to blow, it doesn't quite blow as hard. Maybe it doesn't blow in the same direction that the turbines are facing. There's all kinds of issues associated with that. Solar, sort of the same thing. Increasing common mode unavailability. So what this means is if I have a coal plant and my coal plant fails, it's that coal plant that failed. But when the wind stops blowing, if there's a bunch of turbines sort of in that middle swath of the United States that John talked about, they all can stop blowing at once. That's a common mode failure. It's a common source to the unavailability of a bunch of generators at once, right? Those are getting larger and they're changing from what they were historically. Historically, they might be something like extreme cold. Now we're talking about just drops in wind, cloud cover, things like that. So those types of risks are also changing. And how the system operator has to plan and operate the system has to change along with those because the risk patterns are changing. Less resources available to follow dispatch. One of the things we do at the control center at PJM is we send out signals to generators roughly every 5 minutes saying, go to this output, go to that output, go to this output. The new renewable resources that are coming online typically don't do that in the way that conventional resources used to. So you're sort of replacing conventional resources that were forecastable and controllable with ones that are less forecastable, less controllable. And so from the system operator's perspective, there's less sort of tools in the toolkit to move around and manage fluctuations on the system. Shrinking capacity margin, John talked about that a little bit. I'm going to use the specific term unforced capacity reserve margin. So when I say unforced, what I really mean is the megawatts that are going to show up during the peak load condition, right? So we might get tons and tons of renewables, but if the wind doesn't blow on the peak summer load day, that's a tighter reserve margin, even though on a day like today, we might have tons and tons of megawatts and not really an issue, right? So the capacity story or the reserve margin story is less about the total amount you have, but it's the amount you have during the highest risk period. And I'm going to talk about that when I talk about the capacity market on the next slide. And then just general, this idea of shifting risk patterns. The industry as a whole, since I've been involved in it and even decades before me, has really been focused on this concept of we're going to make sure we have enough for the peak load day, which is typically a summer day for us. And then if we have enough for that, everything else is totally cool. We got no issues. We're good. As long as we're good on that worst, highest peak load day. That is no longer the case. We are still in the PJM footprint, a summer load peaking region. But if you look empirically, the observations would tell you that the risk is not in the summer, it's in the winter. So what's going on? What is that change in the risk pattern from summer to winter? And when you start to introduce resources like solar that can only generate during the daytime, you now shift it from summer daytime to winter nighttime sometimes, which the dynamics around that and the changes in the incentives that need to be set up in the market are pretty drastically different from what we've done sort of historically. And this is really the challenge for folks like me, NERC, ISO, MISO, the areas around the country that sort of do the same thing that at least I do at PJM is, how do we structure the markets to operate in sort of the new world and send the signals that are now a little bit more granular than they were in the past? Maybe they apply to different periods of day, those kinds of things. That's really sort of the challenge of the market designer really across the country. Talk about the capacity market for a second. If you're not familiar with the capacity market, the idea is really it's a call option on energy X years in advance. So today PJM operates a capacity market, and really what we're trying to do is 3 years in advance, we're trying to line up all the resources we need to make sure we can meet the reliability standards we set forth. And I touched on this a little bit on the last slide, but really what's going on is the risk patterns are shifting and the kinds of risks and the way they manifest are shifting too. So let me start on the right side in the top right corner. So for the longest time, reliability just generally from the resource planner's perspective is sort of measured in terms of what's called loss of load expectation. And the idea is really, if I can make sure that we only lose load one time in 10 years, I've hit the standard. That's the standard, right? If you say it's no times, then you sort of have a blank check. So you got to put a boundary on it somewhere. So we say 1 day in 10 years. That was adopted decades and decades ago. And that's really the standard. The thing you start to see is if you look at Winter Storm Uri in Texas, the event in Texas was extremely large. But the metric we use, loss of load expectation, is really based on frequency. So when that one frequency is really big, people get really torqued up about that, a lot of bad consequences. And so what we start to do is investigate different metrics. So if you look at the LOLE that's on the far right corner, the next metric that's most interesting to people, and specifically for PJM, is this concept of EUE, which is expected unserved energy. So I go from LOLE, where I know the number of events that occur in 10 years, and then I switch my metric over to EUE, and I can tell you how many megawatts get lost and when. And so when we look at the size of the events and sort of the distribution of loss of load events, we get a totally different story in terms of resource adequacy and reliability. And so one of the things that's changing in the capacity market and resource adequacy planning is this shift in metrics to look at the magnitude, the distribution of loss of load events to make sure that none of them get incredibly large, to make sure that the incentives are in place to incentivize resources to perform during the events where we might have load shed. And those can occur all over the place. Bottom right corner, what you're really looking at is sort of a heat map of PJM's expected unserved energy. Like I said, historically, we used to plan for the peak period which is a summer load day, and it's that red spot in the bottom right. That's a random day in July, right? Peak load day, we have loss of load risk. What's changing now is that top row going across the top, which says we have also non-zero loss of load risk in the winter, right? Historically, that's not been the case. That is the case now. And so for areas like PJM who have annual capacity markets based on a summer peak load standard, you're losing some information when you don't communicate the problems that are in the winter and the value of performance in the winter. And so we made a capacity market filing back 3 weeks ago, something like that, maybe a month ago in October, to make a bunch of changes to the capacity market to start to move down this path of more granularity in risk identification, more granularity in pricing, and sort of better incentives that drive payments for performance and payments for availability and tie those more closely to the actual risk events as we can identify them, as you see on that chart right there. We're going to keep working on this. We're not done yet. It's a big scope of work. We've done a big chunk and moved in the right direction, but there's more work to go in how we situate the markets around this concept of resource adequacy planning in general. The last topic I'll talk about, the other main push in the market design area is really looking at grid services. John talked about essential reliability services. Ancillary services are sort of a subset of that broader umbrella where we talk about things like reserves. Reserves are just generating capability or load curtailment capability that's on standby in case something unexpected happens. The power industry in general operates on forecast information. It's always wrong, and we need to be able to adapt. And so reserves and these essential reliability services are a little bit the way that we get at that issue of adaptability. Today, I would probably venture to tell you that ancillary service markets really across the US in general are largely underdeveloped because we haven't had to work in the realm of uncertainty that we stand to face in the future. And so there's a lot of work to be done in these grid service markets and how we pay, not for resources to generate electricity, but just to be prepared to do it. Sometimes they take on fixed costs like fuel costs. Sometimes they have to start and operate in a condensing mode or something like that. And so there's a long way to go in how we pay for preparedness and readiness to respond to the uncertainty on the system. Historically, uncertainty hasn't been that bad. It's going to get bigger in the future. And so these grid service markets are really an area where a lot of the different ISO RTOs, and I've got a bunch of different information up there, that they are really focused on how do we make these things more robust so we send the right signals and get the right resources aligned to maintain reliability. So those are the big key points I wanted to get across in my opening comments. Capacity market, energy and reserve markets. Markets are here for reliability. Remember that if nothing else. I'm turning over to Kelly.
Good afternoon, everyone. Thanks for coming out to hear about what I think is a really critical discussion and something that I think going forward, we're going to hear a lot more about, thinking about, what does it actually mean to reliably decarbonize the grid? How do we use the markets that we have? What is this grid? What are the grid operators doing? I think there's a need for people to understand this, especially policymakers, and a need to really think hard about what it's going to take to get to this really moonshot future, right, where we completely decarbonize the grid. So I'm going to talk a little bit about what we've already been discussing. I'm going to walk through what actually is reliability. Why do we have markets for things like reliability, and why do they need fixes all the time? I think that bulk electric system reliability is a public good, and I think we need to start recognizing that and think about how we actually use the institutions that we have, and think about what that means for the market designs that we're working on. And then I'm going to propose a pretty challenging question, which is what if I told you that there's actually nobody in charge of reliably decarbonizing the grid? There's nobody in charge of reliability who is also setting decarbonization targets, and there is nobody in charge of setting decarbonization targets who is also in charge of reliability. There are some possible solutions to this. I think there could be some new market designs we look at, and I think we could look at system planning, particularly regional planning, better. So We've talked about this a little bit, but reliability from NERC's perspective actually has two parts. So we talk a lot about the studies that Adam referenced, looking at what's called resource adequacy. So this is, do you have enough generation resources to meet what you think the expected demand is? And we do lots of pretty sophisticated, what are called loss of load probability risk assessments to say, under various weather conditions, load conditions, what if there's some generator outages, right? There's a lot of assumptions that go into these models to come out with an answer to say, can we meet our 1 in 10, example reliability standard? But there's another part of that. So that's the system planning study that looks out over time in the future. But there's day-to-day operations where the second part of reliability is operating reliability. And this is what's becoming more challenging. So it's making sure that those models sync up to what actually happens in real-time operations. But I think it goes beyond that. So what John mentioned is, withstand sudden disturbances. And that was relatively easy to do when you had a bunch of assets that were dispatchable and they all came with the same kinds of what we've been talking about, these essential reliability services. When you start to move into a future where either those assets are retiring and the new ones coming on don't yet meet those needs, or you have a need to have a decarbonized future and thinking about how do you actually create the machines that can do that. But these are things like, voltage stability, frequency regulation, and actually having balancing resources that can quickly respond to meet changes in supply and demand. So that's the need going into the future. That's the piece that everybody needs to understand. That's the technical piece of how the physics of grid operations happens. And it's really hard to understand what that is, to understand where we're going with policy, and to think about what kinds of markets can enable that. So why did we even start out with markets for resource adequacy in the first place? Well, ultimately we some states deregulated the electricity sector kind of along the same time that they deregulated a lot of other industries. And the idea behind deregulating electricity was that we can use our generation resources much more efficiently and use our transmission lines much more efficiently if we let a market price determine how we do all of this. So the idea is, right, your typical supply and demand curve where you have a bunch of load that's coming on and you have a bunch of generators that can meet that load. And the generator that meets that last increment of load is the one that sets the price. It's called a location-based marginal price, or an LMP. But what was really supposed to happen there was that at times of extreme stress, or at times of really high demand, or at times when you've actually had operating reserves, these are the resources that grid operators hold in reserve. They're not actually generating energy, but they could. When you get to the point where you're starting to have a decline in those resources, the ones that are really, really critical when you're almost about to load shed, the price should be very, very high. That's the idea. It's supposed to be incentivizing generators to come into the market because those prices are high. It's supposed to incentivize them to actually deliver and be there because they want to capture those really high prices. And it's supposed to have consumers be exposed to those really high prices so that they do things too, like stop consuming or find somebody to mitigate and hedge that price risk for them. That was how things were supposed to work. I'll get into a little bit of why it didn't work that way. But essentially, I think the thing to understand is that the idea behind deregulating electricity is that electricity is just a commodity. And all you have to do is think about markets for hedging delivery risk and markets for hedging price risk. And as long as you do that, everything should be fine, under the assumption that it really doesn't matter what kind of resource delivers energy, only that energy is delivered. But as we've been talking about today, and as I showed on the last slide, it actually does matter which kinds of resources are available to deliver energy. Grid operators need resources that have very particular kinds of reliability attributes, and not all resources are the same, and not all resources can provide those same resources. So that's fundamentally, I think, part of the challenge. I won't get into this slide, but this is the reality of what actually happens. So economists talk about market failures, and they talk about two particular elements within electricity, this idea of there's missing markets and there's missing incentives. And if we just fix all of this, we can get it right and we can get back to using markets. But fundamentally, this scarcity price, or this price that needs to be set at times of extreme grid stress, has really never been sufficient to meet reliability targets. It's never worked. And as a result, we've had to have lots of different fixes in these markets. So we have capacity markets, We have what's called an operating reserve demand curve with some administratively set adder to that. So there's lots of fixes that we've had to have in these markets. And what I would like you to take away, I'm not going to, again, go into this, but I can in the questions, is that it's been great to have a price that can enable short-term efficient dispatch in short-term day-to-day grid operations, but relying on that price to be the only investment signal for not just the resources that we want to decarbonize the grid, but for the resources that we need to meet essential reliability services and operating reserves is a problem, and it's been a problem. So again, I think that bulk electric system reliability is a public good, and I'm actually not alone in this. So FERC talked about when they set up these RTOs. So for those of you who don't know, this is an image of where they are in the United States. And even though it doesn't look like they're all over the country, they serve about almost 70% of all consumers are in an area where an RTO exists. And they are, when FERC set them up, they recognize that they are the supplier of last resort for the essential reliability services that are needed to maintain reliability and prevent network system collapse. So that means a blackout. They are the entities that prevent a blackout, and they need to have access to very particular kinds of resources in order to do that. And then I'll also point out that in 2007, there was a task force that looked at wholesale market competition and retail market competition. And the conclusion that they came to in that report that went to Congress was that what grid operators do is the very definition of a public good. So when economists talk about a public good, they talk about it as being both non-exclusive and non-rivalrous. And that is the definition of what grid operators do when they take actions to prevent a blackout. So electricity is also really key to reaching any decarbonization targets. The idea is that we're going to electrify heating, electrify transportation, right? So getting it right in electricity really matters for being able to reach any kind of decarbonization targets. But what we need are resources that meet policy targets and resources that provide the kinds of essential reliability services, that provide the balancing resources that grid operators need to provide this critical public good, as well as they need access to resources that can provide operating reserves. And this is where I started, and I said, what if I told you there's actually nobody in charge of doing this? There are entities that are responsible for reliability, the RTOs that are responsible for meeting the reliability standards that NERC sets. These are mandatory and enforceable, and they have to meet them in order to ensure that we have reliable grid operations. But the RTOs do not set policy. States set policy. So that means that there's really nobody who is thinking about this holistically. And I think that there are some solutions to that, but it requires that we really start to reimagine the institutions that we have and think about how we can use them differently. From a market design perspective, there are some solutions that we can think about. So there's a few things that have been discussed that don't get a lot of discussion in a lot of the stakeholder processes in the RTOs. One of them is maybe thinking about hybrid markets. So these are markets that would recognize, rather than just relying on this short-term market signal that's never worked for the reliability targets that we need, maybe we actually separate that out and say that there's a short-term market signal that enables efficient dispatch, but that's not the signal that we're going to use to enable long-term investment in the kinds of assets that we need, both to meet our decarbonization targets and ensure grid reliability. In that kind of a design, policy is a driver, and it's really informed by system planning. Another option is maybe to think about strategic reserves. So these would be resources that are needed to provide these essential services. We don't have to have every utility have one. Potentially, if you're in an RTO, right, you could actually think about strategically where to put these resources. Everybody pays for these because this is a public good and this is something that's necessary. And as we go forward and have to think about putting on carbon reduction solutions to these assets, maybe there's a way to think about doing this where we collectively, pay for what's needed. But perhaps we think about some kind of a regional integrated resource plan where everybody's thinking collectively about how to plan a regional system. Or maybe there's some other design, but I think it's time we start thinking about those and start having different kinds of conversations than we've been having. And then I'll end with this to say, I think what's really needed is what I call coordinated, reliability informed regional planning. So again, we have very specific resources that are needed. And in order to do this, to have reliability informed planning, I think we should reimagine the role of the RTOs. The RTOs have tremendous system planning capability, and they understand and know what's coming on the system. They understand and know what's needed to maintain reliability. And they are putting out a lot of assessments. They're doing tons of studies to look at, what is the grid in transition? What are the kinds of resources that we need? But what we need is for states to actually use that information and take that information and think about that when they're setting policy targets. I think doing something like that, where the RTOs are providing information and the states are using that information, but the states need to be giving the RTOs, these are our policy targets. This is what we're thinking about for electrification. This is what we're thinking about for bringing in particular kinds of renewables, and have that actually inform regional planning across states who are in these collective, markets. They're not just an individual state. They're actually part of a regional market, and their individual decisions matter for the collective results for this critical public good. So I'll stop there and happy to take questions.
Well, thank you. I think these three presentations provide a very good picture of what is going on, and in some cases, and how this issue has been addressed from the RTO perspective at PJM, but also from the policy side, what could be done, and this is what Kelly explained. But I would like to start this conversation talking about transmission, because John, you explained it was very clearly like the reserve margins are reducing and going down, but there are actually 2,000 gigawatts of total generation capacity, primarily from renewable energy. This is capacity that is right now seeking to be connected to the grid. So there is capacity. To put it in context, we're talking the total capacity installed in the U.S. is 1,200 gigawatts. And in the queue, we have right now 2,000 gigawatts. So there's clearly a bottleneck here. And I wanted you to explain what are the issues concerning transmission. And perhaps, to follow up with Adam, what is PJM doing to streamline this interconnection?
Great. Transmission is a perfect topic of conversation. And before I answer that, I'll describe something that NERC's doing. It was tasked by the U.S. Congress to do. The U.S. Congress has told us to do two things in our history of NERC. One is in 2005, where they said, form yourselves and create reliability standards. The second thing that they told us to do was just a couple months ago, when they asked us to do an interregional transfer capability study. And the whole idea of this is there's been a lot of studies on it, either at DOE or labs at the different RTOs, but there really isn't this comprehensive nationwide look at this transfer capabilities and the opportunities that more transmission has from an independent reliability perspective. A lot has been around costs. These are really needed studies, and the economic studies have shown if we build more transmission and more connections, we can integrate those renewables and deliver them economically. And so that's got some promise. But before we go there, we will not integrate a single megawatt in that queue unless those generator owners pay for the transmission upgrades. That's essentially how we build transmission in this country. In most of the areas, is when there are queued generation, you can certainly interconnect into the grid. It's part of the open access transmission platform that we have, but you have to pay for the transmission upgrades, right? And so you're thinking about a wind generator. Okay, if I'm a wind generator, I got a 100 megawatt plant. I've got to build a transmission line to support that 100 megawatts, because I don't know, my output will vary, but I've got to support that 100 megawatts for that wind. Otherwise, I'll be curtailed, and that's not going to be economic for that unit. Well, the capacity factors on that 100-megawatt plant, capacity factor is how many hours over the course of the year is that actually producing megawatts. It's not very high, 20, 30, maybe 40%. So for a generator owner to think about, well, just to get in the market, I've got to build my stuff, but I also got to build this transmission reinforcement. That puts me out of the market. I can't come up with that. So and so that's kind of that's the current bottleneck. There's just not enough transmission to go around. In order to build that, those megawatts will need more transmission. You can look at other countries, talk to the Germans. They're in the exact same place. They're one of the most progressive places on the country in terms of energy policy. They're trying to build as much wind and solar as they can, and they can't. They cannot build any more wind because where their wind is in the north. It's in the North Sea, and they cannot get that wind to the south where the load is. So you can build wind generation, it'll just be curtailed every single day, right? And it's the same thing with solar. In Germany, a lot of solar plants, been to a couple, and the operators tell me they are curtailed every other day, right? So the Germans, what they've advised us is if you're serious about this transition, start building transmission now. And so there's places to look at that. There are success stories. I look at the CREZ project in Texas. That was they reversed the framework. Instead of build it, they will come. I'm sorry. Instead of they said build it and they will come, right? And so that was a different perspective around how to build transmission. So I think that there's some opportunities there. But building transmission is very difficult, right? Even if we say there's a reason for it, there's an economic, there's a reliability reason for it. Actually doing it is very difficult because of the land use, the restrictions, all of those aspects. So those are my challenges that I had.
So PJM last year, I don't remember exactly when, but in the end of November, we got an order from the FERC to reform our queue process. There's a couple major facets of that. One was sort of streamlining the process and making it faster. The other one was cost certainty. It costs money to go through the queue, right? So we went through a whole queue reform process with our stakeholders to try to speed up the queue and process what was then a backlog. That process will go in place this year. I showed you there's 230,000 megawatts in the queue right now. We expect by the end of 2024 to be able to process something about 65,000 megawatts and then 100,000 megawatts each successive year after that. The other part of the story, though, is why the queue gets backlogged, which is a lot of the projects don't get built. And in some cases, they are sort of speculative to try to sort of feel out where the transmission upgrades are and find the sweet spot. And so you could imagine if you're a planner, rather than processing one project, you get 14. And the way the queue cycles work, when something gets moved out, you have to restudy, and that gets to be sort of a gridlocked kind of process, which is just complicated to begin with. The other thing that I think is worth highlighting is in PJM, at least, there's about 40,000 megawatts of resources that have gone through the queue that are not getting built because of other issues, supply chain, siting, all kinds of stuff like that. So while the queue process, at least in PJM has been updated, can probably be refined even further, that's not the end of the story, because the resources have to get built at the end of the day. And we actually observe in PJM that that's not happening at the rate that they're getting through the queue. So I don't want to dodge the queue issue and say it's not an issue. We can always look for refinements and things like that. But there are issues on the other side of that where resources at times are not getting built. The last point I want to make is regarding interregional transmission. I think it's conceptually a really good idea. The megawatts have to be there to move. And unless we make some changes into the way we look at resource adequacy and risks and things like that, we can have a ton of transmission and no megawatts are going anywhere because they don't exist at the time that you need them. And so both of those have to exist together in order to make the machine work. So I'd urge you just think of both sides of that issue.
And I'm curious, are these sites where these mega coal power stations are retiring, are they getting transformed into solar farms, so to use the available interconnection or not?
I think sometimes they get repurposed for things like solar farms. Sometimes it's repowered to gas. Gas is much more popular than coal now, even though gas is sort of getting unpopular more and more by the day, it seems. So it's a blend of both.
Okay. This is a question for Kelly, and because last week the DOE announced that they are going to directly invest in transmission lines. And this is, I mean, something new because traditionally this is a private business, but because it's been seen as a very risky business, the Biden administration decided to allocate money to directly buy capacity, and that the capacity that they later on they were gonna sell. So Kelly, you mentioned, like, I mean, different ways of decreasing risk. What is your opinion about having the public sector really funding these investments?
Yeah, so I hope everybody caught that. So these were part of the 2005 Energy Policy Act, which gave the DOE the ability to say there are, very specific transmission needs that are needed for reliability purposes, and you have the opportunity to do something about that. There was some legal challenges and reasons why that didn't happen until recently with the Infrastructure Act, fixed that legal challenge, and now the DOE has the ability to serve as an anchor tenant on some of these bigger transmission lines that are helpful, needed, and it helps to de-risk the line itself, because it's kind of like how a pipeline works. So a pipeline works the same way with the anchor tenant concept. So you have people that are going to sign up to use that line, the pipeline. So that's what the DOE did. They're taking a position in the line and saying, there are people who will use this line, and hopefully that enables others to use it as well.
And also follow up of what you mentioned in your presentation, because you said like more coordination in terms of decarbonization policies are required. But we've seen like the EPA bringing a very important regulation to set the standards to fossil fuel power stations. And this is a regulation that is going to accelerate the closure of coal power plants. At the same time, I mean, the capacity may be required. How to really think of I mean, that these regulations get issued or take into consideration reliability issues?
Yeah, so that's the big conversation tomorrow at FERC. There'll be a lot of discussion about the proposed EPA regulations. I will say that one of the interesting responses to what EPA proposed came from a group of RTOs who suggested that maybe one of the things that we need to do is recognize that there are some assets that are needed for reliability purposes, and that some of the technology that may be available at some point is not yet commercial. And if these entities are unable to take advantage of that technology that, helps to make sure that it's low carbon, maybe the RTOs can identify a subset of resources that are needed. One of the things that could do is identify to states which resources are needed, right? So it comes back to this thinking about the role of the RTOs, how that can help inform state policy. So that could make it very clear that, we don't need a ton of resources that have, that are going to be subject to these regulations and may or may not be able to comply and exit, but we do need some. And that could help states identify and understand, this resource over here is needed and it needs to be outfitted with this kind of technology, or you need some other kind of solution.
Okay, I just have two more questions, then we move to the audience, to the question from the audience. And this is for Adam about demand response. And because with the increasing number of distributed resources, for a grid operator, is this an additional challenge to ensure grid reliability, or is it opportunity because you have more resources willing to provide demand response?
Yeah, good question. So Right now, we don't have a ton of, at least as PJM observes it, distributed resources that participate. There was a big FERC to do about it a couple of years ago, and that's sort of in the legal back and forth on how distribution resources can participate in the markets. I think the answer to your question is sort of like it depends on how you do it. And it sort of moves on the spectrum of like observability and controllability. If we observe every piece of equipment moving, we'll have so much data we won't know what to do with it. And if we don't see any of it, then we're probably on the wrong side of the spectrum. So there's probably like this blend in the middle where we get aggregated information, have some controllability over it to where it's both sort of an asset to the control room operator to use for flexibility, and it is a sort of reliability and financial money-making sort of tool for whoever the provider is. Where we end up on that spectrum ultimately, I think, is a little bit up for grabs now, given that it's sort of in the back and forth with FERC right now and the coordination with all the local utilities and things like that.
I talk a little bit about demand response. It's interesting because we've used it typically for, and a lot of the programs are built around residential and commercial AC programs, right? Can people just turn back their dials a little bit? And we're pretty used to that. On the heating side, a little bit harder, right? You kind of don't want to be cold. But think about the new types of resources that we're bringing onto the system. I think about them as pretty advanced, and they're flexible. And so, a Bitcoin mining. Think about Bitcoin mining machines. There's not a correlation for their need to mine and peak demand and or temperatures outside. That's something that can be fully loaded when there's excess generation and can respond, very well to grid signals. I think EVs have that potential. That's probably a little bit further out, especially with range anxiety. But the types of loads that we're bringing on appear to have some opportunity for even more demand response potential. Okay,
and my final question for you, John, because you had a very nice slide that I don't think we were able to see, and that touches on what PJM is doing when reforming capacity markets, and it's about the different characteristics of the generators and what they offer to the grid. And therefore, when we are replacing some with others, like renewables with more traditional, you are affecting other different aspects of grid, and especially grid balancing. So in your view, and I don't know if in your background slide,
which slide were you thinking?
Where you have all this.
Oh yeah, that was a good one. Yeah, it's an eye chart, but you don't need to see the details. This one, yeah.
One. It's difficult to read, but basically it shows like all these characteristics and what they bring to the grid, and which is something that Adam was mentioning when they are reforming these capacity markets, like who is available when and how. But I'm curious about your point of view about the future of gas, because when you see that and the green dots is what what they can offer, gas seems to offer a lot, and therefore, we talk about gas as the bridge to the decarbonization, but it's going to be essential to bring more and more renewables. So.
Yeah, we can't say goodbye to gas quite yet, I think. The gas generators produce electricity. You're spinning metal around copper, right? You're copper around metal, and you're getting all those essential services that you would have gotten from your nuclear or from your coal resources. So as long as you have fuel, an amazing resource, and fast, flexible. We're just worried that around operating during extreme weather temperatures, not the heat, the cold, and making sure the gas is there for everybody.
And I think that's going to be a very difficult realization for a lot of policymakers, that in order to, it doesn't mean we can't get to a decarbonized grid if we have gas today and we have gas for the next 10, 15 years. We can bring on a lot of renewables, we can keep the existing gas units that we have and hopefully get to the point where we have some kind of technology that replaces it in the meantime, or some kind of carbon reduction technology that can be, used with gas. But I think that's the difficult piece for policymakers to understand, that setting certain targets by a certain timeline, right? You can reach net zero, you can reach decarbonization, but this is most likely until you have sufficient batteries that can replace gas, until you have some kind of long duration storage that's capable over multi days, to handle dips in renewables, and especially in the winter, or until you have some other technology, right, that's non-commercial today that can actually replace this asset. That's a hard truth, I think.
Or they hope that new technologies are coming quicker and cheaper so that they could compete. Okay.
One quick on the new technologies, because I can't get past this one. This is great around the carbon reducing measures, and there's certain like CCS designs that we're bringing on for gas, and I think there's some real promise there. The challenge is also these are kind of like unproven technologies. These are additional equipment, additional components to these already finicky machines that have challenges. And the worry is, you add on this stuff, and you probably heard of this quote, right? Complexity is the enemy of reliability, right? So even if the generator is perfect, but we're having some troubles with the CCS portion, well, the whole generator's out, right? And so you have to really understand these new technologies, get used to it, right? It's not just that they're going to be commercially available. You need some operator experience with it. So they learn how to use it. Eventually they'll optimize it, but there is some time to get used to how these new environmental controls might operate in kind of the real world.
Okay, let's get started, Sissy.
I had a question mostly. Question mostly for Adam, but would love to hear others as well. Just on the title of the talk, the role of wholesale markets in preserving reliability. I'm curious. Bulk electric system is one machine. The frequency applies to everyone. You provide mutual aid to other regions, but you have regional markets in a lot of the country. So I'm curious how in PJM, for example, should energy and capacity pricing work when a region like PJM is exporting a substantial amount of energy generated to neighboring regions, especially during extreme weather events?
So you're talking about exports during emergencies, like during Winter Storm Elliott? Is that what you're asking about? Yeah, it's an interesting question. One of the things we went through quite a bit when we talked about the capacity market most recently is this concept of capacity benefit of ties. So it's like the amount of sort of capacity you're willing to rely on your neighbors for, and assume that in your resource adequacy planning. So if I would need 100,000 megawatts and I assume my neighbors can provide 5,000, then I only buy 95 myself, and I sort of rely on my neighbors for that. It is a highly debated concept. And so there's sort of one side of the argument that says, well, it's a public good. You should be able to rely on your neighbor when you can. And so it should offset your costs, and it's cost minimizing for consumers. There's another side of that says, well, does the consumer in PJM really have the right to capacity in MISO? Do they really have the right to have that? Isn't that MISO's loads? Don't they own that? So there's sort of different sides of this argument, sort of from a philosophical perspective. The other thing that gets challenging is there are non-market provisions, specifically in the energy market, around sort of mutual assistance between neighboring areas. And so John gave an example of PJM exporting during Winter Storm Elliott, which was last Christmas time, where we exported. PJM was in an emergency, right? We were exporting to, I think it was TVA, in order to minimize their load shed. Completely a non-market event. Sort of gets people animated in PJM because they're saying, we're paying $4,000 prices and yet you're exporting to somebody else. What gives? Don't we get that? Isn't that our stuff? Then we pay for it. So there's a lot that is, I'll just say left undescribed and ironed out in the markets around this sort of mutual assistance and capacity benefit ties. I know that's kind of a non-answer, but it's sort of an acknowledgement of the issue you're raising around how we handle emergencies and transfers between areas. It's really an area that I think out of Winter Storm Elliott, we probably need to look at. But there were other glaring issues around resource performance and things like that that just took a front seat to that. And so that'll be up on the docket at some point.
Question here.
Thank you, everybody, for the time and the insights. My question, and let me preface it by saying, sorry if it's a bit loaded, but a couple of weeks ago in this very room, the Kleinman Center actually honored the Uruguayan Secretary of Energy for his efforts to convert Uruguay's, system from roughly 50% renewables to almost 98% now. And we praised like all the efforts that they were able to do with their grid, the interconnectedness of their grid. Why is the U.S. so far behind relative to a country like Uruguay in these efforts? We talked a little bit about the technologies that maybe don't exist yet, but again, if we already have these changes in a country like Uruguay, which arguably has less resources, and I understand it's not apples to apples, but what fundamentally is missing here? And again, it's not meant to be like a gotcha question, because I think we're all kind of working towards the same goals and have the same aspirations. But if we can just open the discussion on that point.
Can I ask you a follow-up question, actually? Do you know when Uruguay started?
Sorry?
Do you know when they started?
2009.
2009. Okay.
5 years.
Okay. 5 years.
If I remember, it took about 5 years for that.
Oh, it took them 5 years. So they've been decarbonized for 10.
98%. If I remember the stats, 98% fully on renewables.
Okay.
And they even have the capacity that when, say, like the sun is out, they can rely on solar and let the dams fill up. So there's redundancy even in place.
Gotcha. Thank you for the additional information. Appreciate it.
Anyone wants to take it?
My first thought is just sheer magnitude and size differences. And I want to compare, but around the progress, but just looking at the physical differences, the United States is enormous, and regionally, we don't have access to a very diverse set of resources. And so you mentioned, and I don't know Uruguay's resource mix, but and you said filling dams, but if they've got significant amount of hydro and enough to pair, if they got enough hydro, the same amount as their renewables, man, I wish we had that. I mean, I wish we had more hydro, more pump storage, that we can integrate way more renewables if we had that, because then that's just a big battery. You're pumping water, and you can, one of the best resources for a system operator is a pump storage facility. It's 2,000 megawatts fast. And so even if you have a wind drought, sun's coming up, that resource is a benefit.
And I may add that, Uruguay started with an energy mix with, important hydro capacity that would allow this balancing that here in the US, depending on where you are, it doesn't exist. So that's why there's much more reliance on fossil fuels. But at the same time, one important lesson that we heard from our Carnot Prize awardee was really the political will. They didn't have fossil fuels, and they were depending on exports, very expensive imports. And therefore, there was the political will. Here in the US, the first really federal climate bill just happened last year with the Inflation Reduction Act. So we are lagging, a period of time of a lot of uncertainty. And when there is a lot of uncertainty, it's the worst that can happen to develop business. And I think this uncertainty has, we are paying the price. It's been delayed, but I am positive that we are getting there because technologies are coming along.
I'll throw out a quick speculation, but I'm going to say just generally US politics. If you take the states in PJM as an example. We've got states that want to decarbonize as quickly as possible. We have others that are fighting it to retain coal because it supports the economy within their state. We've got other states in PJM that don't care what provides energy as long as it's at the lowest cost. And that's just like a microcosm of PJM. And I'm sure if you probably went outside, it's probably even wider than that. So I don't know what the political setup in Uruguay is, or whether the grid is sort of owned by the state. I don't know enough about that, but certainly the observation that I would give you from PJM is the parochial interests of the states are often not aligned. And when we have misalignment with the parochial interests, and I'm going to say little guidance at the federal level, I think it gets gridlocked. That would be my controversial response.
And I'll just add on to that to say, I think it's important to recognize that we do not have any national electricity policy in the United States. We do not have anything. We have incentives at the federal level. We have potential EPA regulations, which will set targeted emission, standards in the US, but that is not a national electricity policy. We just don't have one.
This is a question maybe more for thanks. Hi, this is a question maybe more for Adam and PJM. So with interregional transmission, like what type of cost allocation approaches do you guys take for that? And how does that find its way into your work with like wholesale market design and the cost of electricity and things like that?
Yeah, it is a great question that I do not know the answer to. I assume there would be some shared beneficiary principle on the interregional cost allocation. Not knowing planning all that well, I apologize. I don't have a direct answer to your question.
Here, gentlemen.
Thank you. My wife and I drove across the country last summer for the hell of it. We used to do that. I used to be a Stanford professor and our families were back east. So we romantically did a drive across the country. And we were astonished driving through all those red states at the number of wind farms that we saw. As far as you could see, we saw them. And the other thing that was curious to us is very few of them were spinning. And the ones that were spinning very slowly. So we were just puzzling about that. And as we got back more east, I think it might have been in Iowa or Indiana, we came out of breakfast where there were a bunch of good old boys having breakfast in this diner before we were about to hit the road. And a sheriff's car pulled up and everybody clustered around him and they were just chatting away. And I just said, you know what? He's a local guy. So I walked over to the car, I got out of the car, our car, walked over and excused myself, said, excuse me, but I just curious. My wife and I have been driving across the country. We see all these windmills and hardly any of them are spinning. Do you have any idea why? And he said, no. And then the little crowd said, no, didn't know why. And then finally I said, well, I'm just really very curious. And he then said to me, by the way, it ain't for us. He said, we don't get any benefit from this. We mostly just ship it back east. And I said, oh, like the soybeans and the corn and the other stuff that you grow here, but you don't eat it all. You sell it back east. He said, yep. And I said, well, thank you. I'm from Pennsylvania. Keep it coming. Now, here's the question. There must be an easy way for them to ship that. So there must be a national railroad or transmission line or pipeline that they can do that. Else, how could they possibly do that? I'm assuming he was telling the truth that the way they pitch it there, it's just something that they're able to export. So is it in fact there a really good transmission route for electricity? And you're saying no, not even for national defense, not even for defense. There must be some secret grid pathway that we can keep some lab in California going from Maine's hydro. No.
Yeah.
Wow, it's grimmer than I thought.
What I would just say is if the transmission is built for the resources that are being added to it. So there really is no excess. Any additional transmission capacity that's out there is there serving a purpose to meet the reliability standards, right? Because not all transmission lines are on also. So this line might fail. I need to be redundant, I need to be reliable. So yeah, there isn't a secret DC line, but that's exactly what we are trying to study and what is needed to get, up to an interstate level. Got a lot of county roads, got a lot of grid networking that's making the local grids reliable. Not a lot of, PJM to MISO, MISO to SPP, SPP to somewhere in the West. That's really the thing that really needs to be looked at.
Okay, we have time for just one last question in the back.
So this is, I guess, primarily for question that Adam was saying. You spoke a little bit about how decarb targets are, or decarb is not in the same purview as, I guess, reliability. And I was just curious about whether, like, even if we were able to have them both under the same authority, do we know like what the metrics are for reliability? Or because the grid is changing so much, like who's working on that? If we were able to get like all the states to like sit down and put out reliability targets, like how would we know what to make those targets?
Yeah, that's a great question. So that's what NERC does. So NERC actually sets mandatory and enforceable reliability standards for the electric grid, for the bulk grid operators like PJM and the other RTOs. So one of the things that I'm suggesting is that we rely on the RTOs who are subject to these reliability standards to help inform states about what's needed. I think that's a missing coordination link because we have no national policy. I think that's one of the ways that we should think about moving forward.
Just follow up on Kelly's point. We do try to get engaged as much as we are permitted to with the state policymakers as they come up with these policies. There's two issues. One is we're not always invited. And the second one is we give feedback and it's not always taken. So there's sort of a handful of different ways that we try to get involved in these policies, but it's not like anybody is calling us and asking for our sign off on something. It's just not how it works. And in a lot of cases, I think the best we get is we get what we call a reliability out, which is, if you take an example, like take the state of Illinois. Illinois has a policy that says all their gas has to retire by 2035 or 2045, or it has to be powered by some other fuel that doesn't exist yet. In a policy like that, we might be able to work with the state legislature to say, and oh, by the way, if PJM identifies a unit that's needed, it'll be exempted from this policy for a determined time as to be identified by PJM. It's something. It's probably not the end state of where I think we would want to be, but it's a start, and it's better than nothing.
Next week, I'm going to NERC, which is it's like the association of all the state regulatory commissions, and I'm going to talk to them about metrics they need to consider. And so this is top of mind for them. The one thing I want you to think about metrics is there's two parts of a metric. There's one, measuring where are we? What is our adequacy level? The other piece, I think Adam talked a little bit about it. 1 day in 10, we set this years ago, decades ago. That 1 day in 10 is our comfort level, our risk threshold for how we think about how important reliability is to us. 1 day in 10. So you think about when that came up. Well, that was derived when the lights went out. We went to the kitchen and played board games. Right? People weren't like dying in hospitals or at their homes. So you can think about, well, back then, the reliability value proposition was if we had a 1 day in 10, that would be good enough. I tend to think we're more reliant on reliability than we were 4 decades ago. That reliability means more to us, to our health and safety, economic prosper, than just 1 day in 10. So that's the other side of the equation, understanding the design criteria of where we should be. That is, while NERC does it at the national level, the states have that ultimate responsibility and obligation.
Okay, So we're running out of time and we have lunch for everyone outside. So I would like to thank you, all of you, for coming, and to our panelists to have accepted the invitation, and let's give an applause.
Thank you.